Article 2. The Evolution of Neural Networks. From Perceptrons to Transformers. Extended English version on 8,000 characters. Introduction. Neural networks are the beating heart of modern artificial intelligence. Models like GPT, DALL-E, Claude, and Gemini all rely on deep neural architectures that can learn patterns, recognize structures, and perform complex reasoning. But these powerful systems did not appear suddenly. Their evolution spans decades, filled with breakthroughs, failures, rediscoveries, and revolutionary new ideas. In this article, we explore the remarkable journey of neural networks, how they began as simple mathematical models in the 1950s and eventually transformed into the foundation of today's intelligent machines. Phase 1. Birth of the perceptron. The first spark, 1957. In 1957, Frank Rosenblatt introduced the perceptron, the first algorithm inspired directly by biological neurons. What could the perceptron do? Recognize simple patterns, perform binary classification, learn from input-output data. For its time, it was astonishing, a machine that could learn. But its biggest limitation soon became clear. Limitation. The perceptron could only learn linear relationships. Anything nonlinear, including the famous XOR problem, was impossible for it to solve. This weakness would shape the next decade of AI research. Phase 2. The critical blow. Minsky and Papert's bombshell, 1969. In 1969, Marvin Minsky and Seymour Papert published a book mathematically proving that single-layer perceptrons cannot solve nonlinear problems. This discovery caused funding cuts, research labs shutting down, widespread academic disappointment. A 10-year neural network winter began, but this setback would ironically pave the way for a much bigger revolution. Phase 3. Multilayer networks and the rise of backpropagation, 1980s. In the 1980s, researchers discovered that if you add multiple layers and use an algorithm called backpropagation, neural networks could finally learn nonlinear patterns. Why backpropagation changed everything. Enabled training deep layers, allowed learning complex relationships, made neural networks practical again. Multilayer perceptrons, MLPs, gained popularity and showed promising results. The neural network revival had begun, but the world had not seen anything yet. Phase 4. CNN Revolution. Teaching Machines to See, 1990s-2010. Jan LeCun introduced convolutional neural networks, CNNs, which brought a revolution to computer vision. What CNNs can do: recognize objects, detect faces, classify handwritten digits. MNIST. Extract visual features. CNNs can look at images the way humans do, by analyzing local patterns and combining them into larger structures. This architecture became the backbone of modern visual AI, and companies like Facebook, Google, and Apple began adopting it widely. Phase 5. LSTM and GRU, networks that could remember. In natural language processing, the biggest problem was forgetfulness. Traditional networks couldn't carry information across long sequences. Then came LSTM, long short-term memory networks, in the 1990s. They could keep information over time, model long-term dependencies, process sequences like text and speech. LSTM models powered early versions of Google Translate and paved the way for the next generation of language models. Phase 6. The 2012 deep learning explosion. AlexNet changes everything. In 2012, a deep CNN called AlexNet shocked the AI community. It achieved tenfold reduction in error, superhuman image classification skills, massive improvements in speed and accuracy. This was the true beginning of the deep learning era. With the help of GPUs, big data, Advanced optimization, deeper architectures, neural networks began outperforming human-level benchmarks. From speech recognition to medical imaging, deep learning took over the world. Phase 7, the birth of transformers, a true revolution, 2017. In 2017, the landmark paper, Attention is All You Need, introduced the transformer architecture, which changed AI forever. Why transformers were revolutionary? 1. They understand long-range dependencies. 2. Training is massively parallel. 3. They are highly scalable. 4. They work for text, images, audio, and more. 5. They produce rich representations of meaning. Transformers unlocked abilities that were previously impossible and became the foundation of the world's most advanced AI models. Phase 8, the era of large models, GPT and foundation models. OpenAI's GPT series proved that neural networks could evolve into general-purpose intelligent systems. Large neural networks can now understand and generate language, write code, analyze data, produce images, audio and video, reason and solve problems, engage in human-like conversation. Transformers turn neural networks into writers, thinkers, analysts, planners, multimodal generators, autonomous agents. This was not just evolution, it was a revolution. Phase 9, the future of neural networks toward general intelligence. The next generation of neural networks will be more multimodal, more autonomous, more adaptive, more efficient, more aligned with human values. Future networks may learn with little or no data, perceive the world like humans, reason across multiple sensory modalities, make long-term decisions, self-correct, and improve over time. This trajectory may lead toward the first true form of artificial general intelligence, AGI. Conclusion: neural networks have traveled an extraordinary path. 1. Perceptrons. 2. Multilayer networks. 3. CNNs and LSTMs. 4. Deep learning. 5. Transformers. 6. Foundation models like GPT, from a simple mathematical neuron in 1957 to the intelligent systems that shape our modern world. Neural networks have become one of the most transformative technologies in human history, and the future promises even more, because this journey is only beginning.